welcome to Introduction to Nanoscience and Nanotechnology course lecture number 2. I'm Dr. Pervaiz Ahmad. In these lectures, we will have discussions on why nano is interesting. We will discuss the importance of nanoscience or nanomaterials. So let's proceed towards today's lecture. So we have the question to discuss that why nano is interesting. So Nano is interesting because it has some of the remarkable properties, and these remarkable properties are listed as below. For example, we have particles, and those particles they are small, and how small they should be. The smaller scale that we have already mentioned, and we will also discuss that at the end of this lecture. So, at nanoscale, when we have the smaller scale material that is in the range of 1 to 100 nanometer, so there are some special properties which are being associated with the materials. So out of those properties, one of the most important property is the nanomaterial have high surface to volume ratio. So what is mean by high surface to volume ratio? High surface to volume ratio mean that majority of the atom and the nanomaterial they are lying at the surface as compared to the volume. If we take a materials at the nanoscale, so most of the atom they will lie at the surface of the material as compared to the volume. And when the majority of the atom they are at the surface, and it's been mean that the nanomaterial has a larger surface. The volume is small, so majority of the atom they are lying at the surface. So what it mean? It would mean that these material they react differently. So how it react differently? When most of the material they are lying at the surface, so it means that they are exposed to to a larger environment as compared to their bulk counterpart. So it would definitely result in reactivity. So when we have the material at the nanoscale, so they will react differently. Why differently? Because we have larger atom at the surface as compared to the volume, so they are exposed to the larger environment, so they will react differently. So in other words, or in sample words, we can say that the reactivity changes at the nanoscale. And also the material they act differently. If we have a nanoparticles, or we have nanotube, or we have nanosheets, so their properties changes. They will act differently as compared to their normal behaviors, that is when they are at the bulk scale. And along with that they will interact with with light differently. Their optical property change. For example, they may look like red, but when you reduce the size from larger size to smaller size, that is from bulk to nano, so if a material look like red, so at a nanoscale it will look like yellow. So that's why we're saying that the nanoscale material they interact differently with the light, which in simple words mean that the optical properties, that is the properties which is linked with the light, will also change when we reduce the size of the materials from bulk to nano. So we have a question in mind, and that is, are the scale of the small biological structures, it also affect the properties of the biological structure? So definitely yes. The properties of the biological structures, it also changes. If we have smaller biological structures, so their properties are far different than those which if we have it at the larger scale. So the properties of the biological structures, if we are taking that at the nanoscale, so their properties they are changing at the same manner as like the materials. The non-biological material. So at nanoscales, quantum mechanics meet classical mechanics. Just like we have in modern physics or in quantum mechanics, we have Bohr correspondence principles. That is, we say that under certain limits, the classical mechanics or the classical physics is met with the quantum physics or quantum mechanics. So nano is a material, nano is interesting materials, where we say that quantum mechanics meet the classical mechanics. I mean under some conditions, the materials, the material behavior, the material classical behavior meet with the quantum behavior. I mean that this is some of a very good example of the Bohr correspondence principle. I mean, here you can see it practical that how quantum mechanics meet with the classical mechanics. And later on in this course, we will have some real world example for this point. So we have interesting new structures. At the nanoscale, we have interesting new structures, the well-known structures that we will discuss later on in this particular lectures. Those interesting structures included nanoparticle, nanotube, quantum dot, nanowire, nanocylinder, and so many other that also we have to discuss in the coming lectures. So we have interesting materials with nanoparticle embedded. I mean, we have larger scale, we have bulk materials, and we remember those bulk materials, they are made from the smaller building block that we call the nanoparticles. Though that we grow bulk materials, but those bulk materials, since they have the building block, a nanoparticle, so their properties, it's they have the interesting properties of the nanomaterial. And why is that? Because their building block is nano. I mean, though the particles, the material that we grow, the larger size material that we grow, as a whole the material will count as a bulk, larger size material. But since their building block, they are nano, so their properties will be, as interesting as we have that of the nanomaterials and usual nanomaterials. So surface area and energy, what that mean? It mean that just like we mentioned on the previous slide, that as we reduce the size of the material, so the surface or the percentage of the surface atom, it increases. And here you can see it from this particular graph. You can see it here. We are taking it from the paper, and here you can see the link of this paper. And here they have demonstrated that if you have particles, you have nanomaterials, you can see it here. We have plotted the surface atom versus the diameter. So here you can see that when we reduce the diameter, so you can see that under certain edge, the relation is a bit fixed. But when we reach to this particular location, that is 10 nanometers, we are coming below 100 nanometer. So here you can see that we have a rapid increase in the surface atom percentage. This is a practical example. Here you can observe that how the percentage of surface atom increases with the reductions in size or uh, reduction of the diameters. And here you can also see that surface area versus particle size. So what happened? Surface energy increases with the surface area. When we increases, when we reduce the size of the materials, so we basically increase it the surface area. And with the increase in the surface area, the surface energy increases. So along with that, uh, we have what we have large surface energy. So large surface energy mean that the material is unstable. The material instability increases. What it mean? It mean that the material become highly reactive at the nanoscale. So let me repeat it again. When we reduce the size of the material, so it mean that the surface atom percentage, it increases. So when the percentage of the surface atom increases, so it results an increase in the surface energy. So what it mean? The increase in the surface energy mean that the material become unstable, or we can say that the instability of the material increases. So what it mean? It mean that the material is moved toward high reactivity. I mean, driven to grow to reduce surface energy. So I mean, we're trying. I mean, if we move toward the stability, so we trying to adopt some of the technique. I mean, first of all, we I mean, this thing. I mean, the instability of the materials, it is particularly important for the reactivity of the material. So once we are interested in the particular materials, and once we achieve that material, so then we try to drive that to grow it to reduce the surface energy. I mean, once we get that particular material in which we are interested, or once we grow or once we fabricate that particular device in which we are interested, then we trying to adopt the procedure with the help of which we reduce surface energy. I mean, sometimes the people ask the questions that if we have instability due to larger surface energy, so then how we can make the material stable, I mean, to get the required material. So the answer for this is that first of all, we are interested in the reactions of the material. I mean, we perform the reaction according to our own need, and that can be calculated. And later on, I mean, in the coming lectures, we will discuss the procedure that how we can increase or how we can decrease the reactivity of the nanomaterial, or how we can control the instability. I mean, instability, though it's good on one side, is also had the drawback on the other side. So we can increase, by default, the nanomaterials, they have larger surface energy. So by default they are unstable. I mean, they have greater instability. So greater instability can be very good for the reactivity of the materials, but sometimes we need to control that reactivity, particularly when we gain the structure in which we are interested. So physical structure versus physical properties. So we have the questions, that is, what are the structural differences on the nanoscale? I mean, that is particular importance when we are dealing with the physical property of the nanomaterial. So we have physical structures, and those physical structure we judge on the basis of the physical property. And for that, we have put forward a question that what are the structural differences on the nanoscale. So the first structural difference that we have on the nanoscale is a high percentage surface atom. I mean, that we have already discussed on the previous slide, that when we have the reduced size material or low dimensional materials or nanoscale material, so we have a larger percentage of the atom at the surface as compared to the volume. And along with that, we have special confinement. Special confinement mean that since the atom, I mean, they're lying at the surface, so they are confined to a smaller regions. I mean, we have smaller size materials, we have majority of the atom at the surface. So I mean, in the neighborhood, I mean, the due to a smaller size, those materials, they are confined to a particular smaller regions. And due to that confinement, we can sometimes also call as quantum confinement. So due to this quantum confinement, they can interact differently with light. I mean, their mechanical strength increase, and also their other properties like the stress and strain can also be changed due to this confinement. And there are also some special properties which changes due to this special confinement, which which we will discuss later on in the coming lecture. And along with that, once we have a smaller size, so the physical properties that sometimes we call defects or imperfections. So imperfections are also reduced because we are at the smaller scale. So majority of the atom, they are lying at the surface. So by default, when we move from bulk to nano, I mean, we are decreasing the volume by the reduction of size. We are decreasing the volume, so we are coming toward the surface. So by coming toward the surface, it automatically results in the reduction of imperfection or defect. So in sample one, it's mean that we have reduced imperfections at the nanoscale as compared to the bulk. What it mean? It mean that when we are uh, have we when we have the nanoscale material, so nanoscale material, we have low imperfections, we have low defects percentage as compared to the bulk. So one can ask a few more questions, that what properties are affected. I mean, this is a question one might have in their mind when they are dealing or when they are hearing about the nanoscale material. So they can ask the questions, what properties, I mean, what are the more properties which are affected at the nanoscale. So along with that, they can also ask the questions that what properties can we tune. I mean, these are the questions that someone can ask. So properties that change at the nanoscale, they are mostly thermal properties, mechanical properties, electrical properties, and optical properties. I mean, these are the properties which change to a significant range while we reduce the size of the materials from bulk to nano. I mean, when we bring the material at least in one dimensions, uh, between 1 to 100 nanometer, so these are the properties which tunes or which change. And these properties, the first property is thermal property. Thermal property mostly we deal with the melting point or boiling point. I mean, this significantly changed by the reduction of size. And then we have mechanical properties. Mechanical properties, I mean, it's also included, though we didn't mention here it, but it included also stress strain, and also the addition. Addition mean the thickness of the material, so it changes with the size of the material. And then we have the electrical properties. By electrical properties we mean simply the current, but it can also include the conductivity, resistivity, etc. So it also changes by the reduction of size. And along with that, we have the optical properties. The optical properties, we mostly see the prism, so it also changes with the reduction of size, or when you get the material from bulk to nano, so the optical properties also change. I mean, you change the I mean, we can change the refractive index, we can change the absorption, we can change the reflection, refractions, and so many other properties. Are we can also say the transmissions of the light, so it can change. Or we can say that the light, just like we mentioned on the previous slide, that is, light will react differently with the material at the nanoscale than in comparison to the material at the bulk scale. That is, the behavior of the light changes when we have the material at the nanoscale as compared to the bulk. So that what we mean by the optical properties. So here are the example of the nanostructure materials, their size and example. So the nanostructure material, the first type of nanostructure materials, it includes clusters, nanocrystals, and quantum dots. So these are the materials which normally has the diameter, which normally has the radius in the range of 1 to 10 nanometers. And the example of these materials, they might be insulators, they might be semiconductors, they can be metals, and they have normally they have the magnetic. I mean, it can include the magnetic materials as well. I mean, these are the materials which can be found in this particular format. So we have nanoparticles. So nanoparticles, they have all the dimension. They have I mean, they are called zero dimension material. What it mean? It mean that they should have all the dimensions, and the radius range from 1 to 100 nanometers, and that can include their example might be ceramic oxide and buckyball, etc. Then we have nanowires. So nanowires are the material which should have at least one dimension, or we can say the diameter, and that will lie in the range of 1 to 100 nanometers. So nanowire can be metal, semiconductor, oxide, sulfide, and nitride. And we can have nanostructure as nanotubes. Nanotubes, you know that these are the cylindrical structures. I mean, it's like the nanowires, but you know that nanowires are filled, but the nanotube, they are hollow cylindrical structures, and that should have a diameters in the range of 1 to 100 nanometers. So the most popular nanotubes, everybody know about them. They are the carbon nanotubes. Along with that, we have the polarants, layers, halogenides, materials. Nanotubes. We can also have boron nitride nanotubes and boron dope carbon nanotubes, and so many other example exists for the nanotubes. So these are the popular nanostructures we are most familiar with. So that's all we have for this lecture. Hope you enjoyed the lecture. So stay tuned with the next lecture, because next lecture is also important and also interesting, because that lecture, in the next lecture we will discuss some of the questions, some of the very important questions. That is, what is nanoscale science? That is the question that we will deal in the coming lecture. And we will also have to answer the question that how big is a nanometers, and along with that we will try to answer a question that how did we get here. How we reach here, how do we know that nanomaterial is this much interesting, or how, in other words, we will try to understand that how we discover nanoscience or nanotechnology. So stay tuned with the next lecture. See you soon there. Till then, bye bye.